Yes, so it is recording. Yeah, again, a very good morning to all of you. Right, today we are going to start this basic BGT amplifiers. So, previously we are discussing about the DC biasing part of this bipolar junction transistor circuits, and during our discussions, we have also seen why it is so important to set the proper or set the cue point in a proper position. Right. For example, we have seen that this transfer characteristics means output characteristics versus input characteristics, right? And we have seen the characteristics would be some in this way, right? For I am considering the NPN transistor. All right. So if it is like this transistor, then we also know that only this region, which is mentioned here, this forward active. So during this region only, transistor can and act as an amplifier, because here you can see the output versus this input, the slope is greater than 1. Means if you do a small change in the input, then the change in the output would be higher than that, right? And we have seen that suppose if we fix the cue point from here, and then we change this input, so that means basically if you consider now this circuit, so here this VBB is used to set this cue point. On top of VBB, we have superimposed one sinusoidal signal. So this is this sinusoidal signal, right? This is this sinusoidal signal, which you can see from here, right? This one, right? So this sinusoidal signal is changing, right? As a result, you can see this cue point will means the operating point will also move from this position to this position, right? And we have discussed already from this that you will be getting an output, which is V output, which is basically this one, right? It will be in this way fashion, right? So obviously, if you compare the input and the output, the amplitude of this output is higher, and you can see this amplitude, this output is proportional to this input, right? So that means if you take amplitude at any instant of time, this amplitude would be say k times of this input amplitude, right? K times where this k is constant. Means if it is k here in this time instant, then it will be k here in this time instant. It will be k here in this for every time instant it would be k. It would be k. So that's why it is called this linear amplifier, right? Means everywhere you will get the output which is proportional to the input. It will be amplified, but the amplification would be constant. And here also we have noticed that there will be a phase shift for this particular configuration, 180-degree phase shift. You can clearly see it is 0 point time point is here, whereas the 0 time point is here, right? So obviously there is a 180-degree phase shift from here to here. Now the point was, like, instead of keeping this cue point here, if you have suppose taken the cue point here, right, then that is also possible, right? You can change the value of VBB or maybe the other circuit, this VB or this RC, so that you can keep this VBB or this cue point here. So if you are able to keep it here, then on top of which, if you now place this VS, then you see that VS will make a transition like this, right? So you can see here in this region, there will be no application because it is almost flat, right? And it is type means it is actually parallel to this x-axis. So here for this time period, you will not get any output, right? However, for the other section, means for this section, the negative half cycle, you will get an output, and you know the output will be 180-degree phase shift. So that's why for the negative half only, you will be getting the positive half of this output, right? Which is amplified. But you see that this cue point, instead of putting it here, if you place the cue point here, means if change the biasing of this circuit, then the amplification would not be fruitful amplification, right? It would be distorted amplified output, right? So it is very important to keep this cue point. So the DC biasing is almost very important, right? And which is we have understood, and we have also discussed some numerical problems to understand where we should keep this cue point. More understanding of this will also come when we will discuss about this amplifying. Now, you see that the same thing, the same amplification, okay, this we have discussed from this transfer characteristic. The same thing can be also discussed from the output characteristics of a CE amplifier. For example, you can see here this IC is the output current, right? And this is V of CE, right? V of CE here is nothing but this output, right? V of CE here is nothing but this output. right? And what is IC? IC is the current which is simply flowing through this, right? So we know that this IC versus V of C characteristics would be like this, right? And here we have also seen how to draw this load line, and say the Q point we have fixed this initially to this point, right? So we have set this other parameters such that the Q point is almost at the middle of this Q point, right? Now, okay, now again consider this circuit. Okay, so VBB, which you have chosen VBB such that the Q point is here. Now on top of this VBB, you have one sinusoidal signal as well. So this sinusoidal signal will change, right? So this sinusoidal signal, when the sinusoidal signal will change, that will also change the IB, right? So IB, if you do not consider this VS, then IB is only due to VBB, DC source. But now you have superimposed an AC signal on top of it, right? So the value of this here, this potential is also changing. So as a result, IB will also change. So during this point, IB would be maximum. During this point, IB would be minimum, right? And this point, IB would be same as this of this DC value, VBB. Say this is that Q point, right? Now you are changing this IB. So IB, suppose you have changed, you are changing it from like this, huh? Like this. So IB is changing from 0 to here, right? So here you can see this basically then IB you have changed from this IB3 to IB4 to IB2, right? Within this range, right? So as a result, how this IC will change? So IC will do it. IC will also do a transition similar to like this IB only, right? IC will do a change also similar to that of this IB, right? But say this beta value for this transistor is 100, right? So that means what is the level of this IB compared to that? This level, this IC, change in IC would be 100 times, right? That we have understood. Okay. Now see how that is being reflected in the output or V of CE. So for that, if you see from here, this IC is changing like this, right? So again, if you take a, this is the type of graphically plotting this. So if you take a reflection from here and suppose you are plotting it from here, right? Then for this point, reflection is here. Then if you, and this is time t equal to 0, right? And here, this is time t equal to 0. And the time is increasing in this direction, right? Now let us come to this point. So this point corresponds to here, then this point. Let us then come to this point. This point corresponds to here, then this point corresponds to here, then this point, take a reflection along, this point, right? This point, take a reflection along this line, and they should come here, right? So that way you see this output is like this, right? So here also you can see this here, right? Compared to IB, this IB and IC, they are in the same phase, right? But if you see the IC, if you compare this V of C or the output, right? V of C or this out, this is the same as output, right? They are again in the out of phase, right? So it is possible, means the same thing graphically, which we have explained from this transfer characteristics, you can do the same thing from this output characteristics as well, right? And you can also understand from here why this there will be 180-degree phase shift, right? Now, the thing is that when we are analyzing this type of circuit, right, then we have considered that this circuit is to be linear, right? And when we have considered that this circuit is linear, then only we can apply the superposition theorem. So that means we can separately analyze the circuit performance in DC, right, and then in AC, right? We have to do that, right? So that means first we will analyze the circuit in DC analysis and see where is the Q point, right? And once we have understood what is the Q point and what is the current at this Q point, then we should do the AC analysis, right? And for that, this circuit is have to be linear circuit, right? Now, if you consider here this IB, which is the input here for for this case, now how this IB, I mean, why this IB is basically changing? IB is changing because you are changing VS, right? So what does that mean? This VS, VS is the reason for which this IB is changing. So when this VS is changing, so basically you are changing this V of BE, right? Actually, you are changing this voltage across this, and that's why your IB is changing, right? Now let us see what is the, again, come back and discuss this. I think we have discussed it a couple of times. See, what is the relation between IB and V of BE? So this is basically a diode, right? If you consider this, this one, right? So here this IB and the relation between V of BE is nothing but a diode relation, right? So the expected characteristics would be exponential like this. So suppose the Q point, you have fixed it here. Okay, this is the Q point. So this is the Q point. Okay, and this is due to this. Okay, let me not write it like 1 minute. Where is the view? Toolbars. Standard. Eraser option is not visible. Now it is here. So let me not write it as VBB, but let me write it as Q point. Okay, means Q point for V of B. Right? We have fixed this Q point here for this circuit. Right? We have fixed this Q point. Means the DC value is V of B. Right? This capital V, capital B, capital E. Right? And the total value means AC plus DC is, we are representing it by this symbol. So there is a small difference, right? Okay. Now you see, if you are changing this input, right, means VB is, you are changing it like this, then the output will change. From this figure, you can see this output will change like this, right? It is very easy to understand, right? You do a small change in input, then the output will also change, right? But how the output will change? See, if this input, the amplitude of this, okay, the change is very small, then for this you can consider the slope is not changing. This basically you can consider it as to be a linear one. So if you consider to be a linear one for this region, right, then you can say this output would be linearly related with the change in this input. So are you getting my point? So we know that IB is proportional to exponential of V of BE by VT, right? This is the way this IB is related. But if you consider only for a very small region, okay, and to get this very small region, you have to restrict the change in V of B to a very very small value. Then you can consider this is a straight line, and in there you can assume here this IB is proportional to V of B. So if you can assume, then for that particular criteria, you can assume then this transistor is behaving as a linear network, right? And then you can apply the superposition theorem, right? So you have understood one thing, that the amplitude of this change has to be very small. So that particular term, or the small that signal, the change in that signal is called the small signal. Okay, that particular signal is called small signal. So now in the next page, let us discuss it a bit more. Sir, what do we mean by the small signal, and what should be the value of that small signal? Yes.
Excuse me, sir. If we apply KVL, then we are getting a different variation of IB with VBE.
If we are applying KVL, then you are getting different variation of IB.
With VBE means it will be linearly decreasing with respect to VBE.
No, but how can you do it? Because you know that this one is actually, we take it type of constant, right? 0.7, but actually is it a constant? See,
Like, sir, even if we do not assume it to be constant, then VBB minus VBE is equal to IBRB. We can write this equation.
VBB minus V of B equal to IBRB. Okay, then
IB is varying with VB in a different sense. It is not linearly proportional, like it is proportional to minus VBE. And from the graph, we are getting it proportional to plus VBE.
from the, no, why? I think you are doing some mistake. Okay, let us check it. So from here, what you are saying is that VBB, okay, let us say VS is not there, okay, equal to IBRB plus V of B. Okay, then
Sir, now we plot, if we plot the graph of IB versus VB, then the graph will not look like what we have drawn in the lower portion of the page.
what we are drawing in the lower portion of this, okay,
Means it is linearly increasing, no? But how it is increasing with respect? If
okay,
we
but
increase
here,
VB,
1 minute, in this equation, can you change V of B in this equation?
means KVL we have applied, we have
Yes,
not made any
KVL
effort.
you can apply definitely, but there in KVL, this equation would be true. But my question is, can you change V of B here? Or always we have taken for DC like it is around 0.7 fixed at,
For
isn't it?
problem solving, we have assumed it to be to 0.7.
0.7, right? For DC analysis, right? Okay. But now say that you have a small change in this V of BB, huh? Small change. Okay. Then that is going to impact this V of B as well, isn't it? Now, how this V of B is related with IB, right? Are you getting my point? When you are
Yes.
writing KVL, this one, there you cannot actually take change this V of B like this, because V of B you have taken constant and you have assumed that V of B is not changing. That's why you have taken, you can write this equation. But if you have to change this V of B, you have to take care of this IB as well, because IB will change exponentially with V of B.
Okay,
So,
sir.
so this one will give us the load line, right?
Yes, this is basically, this will give you the load line, right?
And we can get the Q point through the
They will get
intersection
the
of
Q point. This is not for this here. You cannot change that value of V of B. Okay, so you understand then the signal has to be small. Signal means the change across V of BE, this signal, right? The drop across V of B due to this VS has to be small. Remember that. It is not, we are not talking about what is the value of this VS, but we are talking about the value of this V of BE. That is, that will be, which will result because of this small V of S or the sinusoidal signal. So again, to discuss like what is the small signal and what should be the actual value of that small signal, then let us again start with the same diagram that we have seen in the last page. So here IB versus V of BE plot and the same characteristics, this diode plot, right? And here if we assume this region to be an straight line, because then we have to also consider the change in V of B is quite small, right? And this is the initial Q point, and this is basically the change. This portion is due to this portion of change in V of BE is due to the change in the sinusoidal signal, right? Now, before we start our discussion, let us go to the next page and discuss this thing, notation, right? So for during this part here, we will change our notation, or we will use some different notations, and where we have to remember these notations, okay, so that we avoid any confusion. So total instantaneous value, so you remember earlier we are writing this IB, I capital C, V of BE, small v, capital V of B, V of C, all these are total instantaneous value. So that means it includes both DC as well as AC. Right. Now, when you consider the only the DC value, then you have to write IB, IC, V of BE, V of C. We will denote these DC values by all caps, right? I also caps, the subscripts are also caps. Then instantaneous AC values. This instantaneous AC value, we will represent it like this: small I, small b, small I, small c, small v, small b, small e, this one C, E. Okay, so please remember these notations, and these notations we will be using during this amplifier design. And the same notation is also been used in your book. So I am not changing these notations. I am using exactly the same notation, okay, which has been used in your book. Fine. Okay. Right. So now, if you consider what is the slope of this region, right? If this is a straight line, then it should have also have a slope. So what is the slope? Slope will be equal to this 1 by RD only, right? For the time being, you just forget about this one. Okay. So this, what is the slope? Slope is nothing but 1 by RD. What is 1 by RD? 1 by RD, this where this RD is what? RD is the resistance, right? It is basically the diode AC resistance, this part, right? And it is equal to 1 by, this is the slope, right? And you know that any IV characteristics, the slope is 1 by resistance only, right? Okay. Then let us write couple of equations from then see from this equation what can we comment on this small v, small b, small e, right? Okay. So to start with, let us write this IB, and you know what this notation means. It is the total value of current, base current, IB. This is equal to IS by beta into exponential of V of BE by VT. Okay, right? This equation we have already discussed during our diode, like during our BJT DC analysis part. Remember, we are neglecting -1, and because we are considering V of BE is at least greater than 3 times of VT, right? Then we can neglect this -1 term, right? So if it is true, and here for this particular circuit, right, we can say this V of BE total instantaneous value is because of these two, right? Because one is the due to the DC part and the other one is due to the AC part, or the small signal part. So we can write here that this V of E total value is equal to V of BE plus small v, small b, small e.
Sir,
Right?
what is IS in the IB equation?
This is the reverse this inverse leakage current for
Okay.
this collector current. Means we write collect.
Yes,
We have represented collector current like this: IS exponential of V of BE by VT. Right, and we know this IB is equal to IB is equal to IC by beta. So that way you can write it like this.
yes.
Okay.
Yes.
So here just write this IB equal to, just substitute. We are just going to substitute it. V of B small v this E by VT. Then we will write it like IB, IS by beta exponential of V of BE by VT into just we will separate out these two, right? VT. Now what is this part? See, this is the collect. This is basically the base current, right? Due to the DC volt supply voltage only, or other way you can say that this is the IBQ. So I'm writing it. You please check it out. This is IBQ. Can you not write it IBQ? Yes, IBQ into uh, exponential of V of BE by VT. Is this part clear to you? It should be, right, because it is easy only. Right. From here, to save some space, we are doing now going to this side. Okay. Now, this see, if this is exponential function, okay, this is an basically exponential of x, right? And here, if say this V of B is less than VT, or say much less than VT, or less, it is basically less than 1, then we can neglect the higher order terms. Okay, or maybe let me write it. See, e to the power x. How can we write this exponential e to the power, means e to the power x in series, Taylor series? It is 1 plus x square by 2 plus x cube by 6 plus dot dot dot, right? Okay. Now, if this x is less than 1, then this part square, cube, and the higher order terms, this can be neglected. isn't it? Then this part can be neglected. Okay. If it is so, then we can take only these first two terms. So IBQ into 1 plus V of BE by VT. Right? Okay. So what is this IB? IB is again the total instant means total instantaneous value. So that also you can write it as IBQ plus small I small b, right? So this is IBQ plus IBQ into V of BE by VT. So IBQ, so you can see we can cancel it out. So you can write IB equal to IBQ into V of BE by VT, right? So basically, if we use this assumption, that is x is less than 1, then what we can write that IB is proportional to V of BE, right? That linear one means that linear relation we can establish, right? So now what do we mean by x less than 1? Now x less than 1 here, x means here V of BE by VT is less than 1. So that means V of BE is less than VT, right? So this is the condition, okay, for which you can establish, you can get a linear relationship between input and output, right? Okay, to further discuss it in bit more. Now, what is the value of VT at room temperature? It is 26 millivolt, right? At 300 K. So that means change in V of BE or change in this potential, change in this potential, right? Change in this potential should not be more than 26 millivolt at room temperature, right? Then only we can get that linear relation between the input current and between this IB and V of BE, right? Okay. Now, there is a, the thumb rule that generally, or the rule of thumb generally that we use is that V of BE, we will always try to restrict it below 10 millivolt. Okay. So V of B is less than, should be 10 millivolt. Okay. Then only we will assume that IB would have a linear relation with V of B. Right. I hope the criteria is clear to you. Now see the how we are using this criteria. See, now IB is proportional to this V of B. So this is a linear relation, right? Okay. Now what is V of B? V of B is again will be proportional to the this V of S, isn't it? Just think about it. If this V of is more, then V of B will also be more, right? And because this V of B is on entirely due to the change in Vs only, right? So again, this is the linear relationship. So that way you can say IB is proportionate to linearly related to this Vs, right? So the with this input, the output means the IB is linear, right? Okay. Then we know this IC. IC equal to beta of IB, right? This is if we consider that beta is constant, and for most of our active region we can consider that. So that way we can say IC is linearly related to IB. So that way again IC is linearly related with this Vs input signal, right? Okay. Now what is this output? Okay, for this particular case, so 1 minute. For this particular case, what is this output voltage? Output voltage is equal to VCC minus ICRC, right? Even you will see later on that this relation holds, okay, for AC analysis as well. So here, then we can also write this, V output equal to this VCC minus this, this IC into RC, right? Now here, this IC is again linearly related with this Vs. So that way output voltage is also now linearly related with the input voltage. So you see that all the relationship now what we are discussing, output to input, they are now becoming linear, even though the basic relations for this bipolar junction transistor between IV and V of BE is an exponential one. But we are doing the approximations, and we are taking this criteria such that only this part has to be considered. This part, the remaining part can be neglected if this x is less than 1. So we have got the criteria from here, and we have seen the rule of thumb is V of B is less than 10 millivolt. Is that clear to you? Clear, right? Okay. So here,
Excuse me, sir.
हाँ बोलो.
Sir, this V naught is equal to VCC minus ICRC.
Right. So here again, here we are considering, see, in this, where is it? Here, this output, we are considering the total output. Okay. So give me some time, you will understand why I am writing here the total output. Okay. Because if it is a small signal output, because we have not discussed what is a small signal output so far, so it will be difficult for you to understand right at this moment. But you can say, see, what is the total I, sorry, what is this IC? Total I capital C, instantaneous current, it will be capital IC plus small ic, right? So if you say like capital IC is constant, then this instantaneous total IC would also be proportional to this, isn't it? So that way, this output voltage would be also proportional to this this IC, this instantaneous IC, and this IC is again proportional to the small IC, right? Okay. So now, so far we have neglected this part, right? This part neglected. Now let us also consider what would have happened if we have considered this part. What would have happened means if this x is not less than 0. Yes. Do you have a question?
Yes, sir. Sir, I did not understand the approximation because original formula is exp VB by VT minus 1.
Right.
And we are neglecting minus 1 by stating that VB is large. And now we are stating VB to be small and neglecting minus 1 as well.
Yes. See, what is this V of BE? What is this V of BE? This is the total value, right? So that means V of B is due to that AC part plus DC part, right? So I should have make this notation bit carefully. This should be like this. Right? So you see from here, this V of B, right? This one is equal to this DC part plus the AC part, right? Now the overall, this total thing, this will be close to 0.close to, right? Close to 0.7 volt only, right? And 0.7 volt is much higher than 0.26 volt, which is nothing but VT, right? So we are doing the approximation because of that. That's why we are neglecting here this minus 1.
Okay, sir, understood.
Understood? Okay.
Yes.
Sir, but below we find that it should be almost equal to 26 millivolt.
Below?
Okay, yes, sir, got sir. Means there was a DC component.
Okay. So let us now say, like, what would have happened if we have not neglected this part, right? Or even we are taking the first two parts, means is there any effect, right? Say we are saying like x is less than 1, then we can do this assumption, right? 1 plus x. But this less than 1 means, like as I mentioned, V of B is less than VT. So that means 26 millivolt. You could have taken 1 millivolt, right? Then also this criteria is satisfied. You would have taken 25 millivolt. Then also this criteria would have been satisfied, right? But the effect, whether the input is of 1 millivolt or 25 millivolt, the effect would be different, or the approximation or the validity of the approximation would be different, right? So let us check it out. So here, what we are doing, we are writing this exponential, this Taylor series expansion once again, x square plus 2, x square by 2, x cube by 6 plus dot dot dot. And let us say now this time, okay, and let us say now this time we will not neglect any of the terms. Okay, so we'll consider all the terms. Okay, and here what is x? Remember here, this what is x? This x is v of b by vt, isn't it? X is equal to v of be by vt. Now what is v of b? Say like the source signal is of sinusoidal signal, and so you can write it is vm sine of omega t, right? This is any arbitrary signal, but it say it is a sinusoidal signal. Okay. Now again, why, most of the time we will consider our signal to be like our input signal to be sinusoidal signal, because any arbitrary signal, can be represented in terms of sinusoidal signal, means some addition of sinusoidal signal. Okay, suppose you have some arbitrary signal, okay, like suppose this type of signal, okay, with respect to time, then this signal also can be written as a summation of different sinusoidal signal of different amplitudes, different frequency. Fine. So that's what it is quite common practice to consider sinusoidal signal to be considered as an input signal. Okay, so you see this x equal to this this one. So let us now write that the total thing here. Okay, then this e to the power x, we can write it as this 1 plus Vm sine of omega t by Vt plus this Vm square sine square omega t by here it was 2, so 2 Vt square plus this Vm by Vt, that cube, into sine cube omega t by here there was a 6 plus dot dot dot. So we are not considering the higher, but you could have considered that, because we just want to see what would be the effect of this x square and x cube, okay, in this. So here it would be 1 plus this Vm sine of omega t by Vt plus this is Vm square by 2 Vt square, right? See, this is sine square omega t, right? Sine square omega t can be written as like half of 1 minus cos of 2 omega t, right? And 1 minus cos of 2 omega t can be written as the sine of this 2 omega t plus 90 degree, right? So we can write it like, so we have to write another half. So here half, then here 1 minus sine of 2 omega t plus 90 degree. Yeah, I think I have written everything, Vm square 2 Vt. So this part is done and this part is taken care by this part. Okay. Now, similarly, this sine cube, right? Sine cube also can be written, sine of 3 omega t, right? 3 sine omega t minus, like you can expand sine of 3 omega t, right? Then you have a term of this sine cube omega t. So sine cube omega t, you can write in terms of this, that formula, right? So if you do that, then it would come like this. So it is Vm by Vt, this into 1 by 6. Now I am writing this part. This part would be 1 by 4, 3 sine of omega t minus sine of 3 omega t. Right. So here, just if you now arrange this part a bit more carefully, then let us pick this part. Okay, this terms without sine of omega t. So one would be here, and there would be another term like this. One would be here, and the other is this, right? So let us pick these two. 1 plus 1 by 4 Gm by pi t. This is square, right? So this is basically the DC part, right? No sinusoidal signal is involved with this, right? And here it is Vm by Vt into 1 plus 1 by 8 this is square into sine of omega t sorry, I think I will need much more space here. So here it is 1 by 4. This is Vm by Vt square into sine of 2 omega t plus 90 degree minus now we will try to cover up the sine of 3 omega t. So it is Vm by Vt, right? 24 Vm by Vt, that cube sine of 3 omega t, right? Now notice carefully here. So whatever you have given, you are basically doing this exponential of Vm sine of omega t by Vt. You are basically expanding this one, right? And what you have got, this plus dot dot dot, right? This is up to like cube, right? You could have got the higher orders as taken the higher order as well. So you have seen. So this is that DC part, right? You can say that this is that DC part. This is without sine of omega t. This is not dependent on the omega, right? Now this is sine of omega t. See, your signal is actually sine of omega t, right? So this is sine of omega t, right? So this is what the same similar signal you are getting here. But see, what is the difference? The difference is here, the sine of omega t, if you consider the first part, it is Vm by Vt sine of omega t. Okay, this is the type of the same thing. Like, or you can say that this is the linear part. But what about this Vm by Vt, that square, right? Again, this is not a linear relation, right? So you are expanding it, but what you are getting is actually not a linear part. Now, if you see other than this sine of omega t, then you see this 2 sine of omega t, where your frequency is expected to be omega, but you are getting a additional, if you like, because of this expansion, you are getting a term which is of 2 sine omega t. At the same time, you are also getting 3 sine omega t, right? So these terms are called the harmonics. Okay, so harmonics means basically if your actual signal frequency is omega, then the 2 omega is called the second harmonic, 3 omega is called the third harmonic, like that, right? And it is very difficult to suppress this harmonics, okay, from the actual signal. And also, if you are lucky enough that you could have done this harmonic, like separate out, but you see that even that sine of omega t, right, you have some term which is also not linear, right? So that means even this approximation that we are doing, that e to the power x only this first term, we also have some error involved in that. Okay, so it is also not free from any or the results what we are getting is not absolutely correct result. Here also some error is also involved because of our approximation. But if we can able to make this x to be very less than 1, yes, then the error in that would be significantly reduced. So I hope this harmonic portion is clear to you, what is called this harmonic and where from these harmonics are coming, right? And due to this presence of this harmonic, a figure of an issue will come, that is called this harmonic distortion. Right? That means together with omega, you will also get 2 omega, 3 omega, like multiple of this omega. And here, before we end this topic, so here one figure of merit has been also discussed, that is called the total harmonic distortion. And this is always represented in percentage. So that is quite easy to remember. This is basically the summation of all, square root summation of all these amplitudes. Say this, this amplitude, right? This amplitude, like summation of all this amplitude square, and then root over, right? And so this will be starting from the second harmonic to, suppose if you have nth harmonic to nth, so nth harmonic, okay, of this Vn, and divided by this V1. V1 term is basically this one. The first term is V1, this one. This value is V1. So divided by V1. So you are adding from here all these amplitudes hereafter, right? And seeing that what is the percentage of this amplitude compared to the amplitude of this part, sine of omega t, right? Into 100%. Okay. And in your book, we are not going in much more detail of this because this is not that way important for this particular course. So if you plot this total harmonic distortion in percentage, and if you have this, say this V of BE, right, then the total harmonic distortion plot would look something like where it will actually increase linearly. Right. So if you have, then you can see clearly, if you have more V of BE, right, then you will have more harmonic distortions. Right. So it is expected that to get a less harmonic distortion, you should always reduce this V of BE, and eventually you suppose if it is 10 millivolt, right, then for this 10 millivolt you will be getting a total harmonic distortion which is less than 10. Okay, so 10 should be a little bit above, so it, because it is less than 10. Okay. Okay, I hope this part is clear. This is not difficult to understand. Just this is what is most important for us, is what should be the value of this V of BE. If you have understood this part, then I think that is sufficient for this course. And the remaining part, like harmonics, you understood like what is called means what do you mean by harmonic? How do you mean by harmonic distortion? And why these harmonics are coming? Okay, and how these harmonics are related with the value of this V of BE.
Sir, won't the value of V1 and V2 change if we take more terms?
On the value of V1 and V2 will change if we take more terms. Okay, can you please try it out? That is a very good question. X to the power 4. Okay, then this. See, then it will become sine to the power 4 by 90. I mean, sine to the power 4, right?
Yes, sir.
Huh? I mean,
Yes, sir.
sine x to the power 4, right? So you try to expand that, okay, and see that if you are getting any term related of sine of omega t or sine squared omega t, or a term without sine, it might come. It might come. Then, yeah, that, but those terms, if these terms are also coming, if you are going from this side to, means for higher and higher value, those terms, these coefficients would become bit more less significant. Okay, so you can see from here, that is also, see this. This is Vm by 2 Vt, right? So it is Vm by 2 Vt. So, Vm is itself a bit less than this Vt, right? So that way, this term is less than 1, right? So it is less, a term which is less than 1, you are taking square of this. And for the third harmonic, you are taking a term which is less than 1, you are making a cube. So obviously these values are reducing, right? The magnitudes are reducing for the higher orders. Okay, so you might get, but the values might be reduced. So notations, I think we
Sir?
have.
Sir, how is the graph of THD versus VBE? Is it linear?
How this portion has been linear. So, okay, if you have calculated this part, the total part, okay, and added this thing, then you will get also this, you will get a linear curve only actually. Now your question is why it is linear curve? Then you have to first add all these things, okay, then compare it with this V1, right? And what is V1? V1 is related with this Vm. And is it very difficult to understand that that with increase in Vm, the total harmonic total harmonic distortion will increase, right? So increase, you can clearly say, right? It will increase. But now your question is why the curve should be linear. Okay. So can you put a try? So can you please check it out? Like at least for this first two terms. Okay. This is V1, this is V2, this is V3. Okay. So can you please check it? No, maybe not now in your home, and maybe you can tell next day, right? So you, if you are doing it like this, then are you getting a linear curve or not? Okay. Yeah, I think it's already 10:55, but now if I start this one, and even I would not be able to complete it. So I think okay, we will take it up in the next class. Okay, I thought okay, eventually I thought of putting one example, but yeah. Anyway, so yeah, I think we will continue from here in the next class. Okay, small signal hybrid pi equivalent circuit. So here, see, so far what we have done, we have understood what do you mean by small signal, right? Now, and we are also aware how to do the DC analysis, right? And to find the Q points, right? That part is now done. Now the thing is that if we comply with the small signal, right? I mean, if the signal is small enough so that we can consider the network to be a linear one, right? Then this particular bipolar junction transistor can be represented in represented by some equivalent circuit. Okay, and this type of equivalent, there are a couple of different ways you can represent. Means you can say like there are different models by which you represent. So one of such representation is called this hybrid pi model. So hybrid pi model is basically is called the H parameter model of this bipolar junction transistor. So this bipolar junction transistor can be treated as an again, see, if it is plus, then it is negative, so you can consider it as to be this one as a ground, right? And this is another network. So this is one. If you say that this is V1, and say the output here is this V2, right? And you say that this input here is IB, this output here is IC, then this transistor can be represented by a two-port network, right? Where it is V1, this is V2, this is I1, this is I2, like that. Okay, transistor can be represented means in it by a two-port network. And any two-port network means when you have a two-port network, you can represent the two-port network by different parameters, by its impedance parameter, admittance parameter, ABCD parameter, H parameter, like that, G parameter. So this H parameter, when you are using this H parameter, then only it is called this hybrid pi model. Why pi? Because you will see that, okay, maybe I will show you. The ultimate, equivalent circuit would look something like this. Okay, it is not complete. I thought of completing in front of you. So, but it's basically shape would look like this. So it is basically, the inverted pi. So it is pi. And why it is called hybrid? Because you can see here, you have an equivalent resistance one, and you will see that you will have an here GM, transconductance part. So you have resistance, conductance part together. Okay. In fact, in H parameter case, you will also see its voltage gain along with this resistances and conductance. You will also see its voltage gain and current gain. So in H parameter, everything is type of mixed. No, so it is called this hybrid. But if you consider like type of Z parameter, then in Z parameter it is like everything is represented by its impedance. If it is the admittance parameter, then everything is represented by that way. But in H parameter or in H network, like you have all these different terms: resistance, conductance, current gain, voltage gain, in all this. But like for our bipolar junction transistor case, we will see that the simplified circuit can be represented by this form. Okay, or in this way we can represent it. So you can see basically like this bipolar junction transistor. Okay, this thing now has been represented by simple resistance and current source. Okay, see, nothing else is here. Okay. So we'll see that, okay, how we can represent or how we can come from this bipolar junction transistor to this particular circuit. And if we can come to this circuit, then what should be the value of this R pi and what should be the value of this GM? Okay. So then once we have understood like what is the small signal circuit, then we will come to a small example where we will see that how we can find the small signal gain, okay, of this circuit, okay, so that we can understand the process, okay, the complete process. Okay, then we will take some bit complicated amplifier, means a little bit more complicated amplifier structure and try to analyze those. Okay. Okay then. So we'll start from here in the next class. Okay. Thank you.
Thank you, sir.
Yes, you are welcome.
Thank you, sir.
Thank you, sir.